What if one of the foundational laws of physics, something taught in every classroom, encoded in every satellite launch, and used to predict the orbits of planets for over 300 years, is now showing cracks? That's not a fringe conspiracy, but a growing whisper among astrophysicists after shocking new data from the James Webb Space Telescope and multiple Earth-based observatories began pointing at one unlikely culprit, Neptune. Yes, Neptune, the distant icy giant long thought to be a quiet, predictable sentinel at the edge of our solar system, may be violating Newton's laws of motion in ways no one can fully explain. But how can that be? The laws of Newton have predicted planetary movements with astonishing accuracy, even leading to the discovery of Neptune itself in 1846. But now this same planet appears to be straying subtly, yet consistently from the path that Newton's equations would expect. Neil deGrasse Tyson recently broke this stunning development in a statement that sent ripples through the scientific community. Neptune's orbit, he says, doesn't entirely obey classical physics anymore. At first, that might sound like an exaggeration, or even a misreading of instruments. But the numbers collected from the JWST, the ALMA array in Chile, and the Very Large Array in New Mexico are hard to ignore. These aren't mere measurement errors. They are repeated, cross-verified anomalies that hint at a deeper mystery. So what's going on inside Neptune? Could this icy world be hiding a form of matter that defies everything we know about how the universe is structured? According to new hypotheses, Neptune's interior may not be a uniform shell of gas and ice, but a far more complex matrix of superionic states. Dynamic plasma flows, and even exotic matter that has only ever been theorized in particle accelerators. These strange inner materials might be shifting Neptune's gravitational center subtly over time, causing the planet to wobble imperceptibly to the naked eye, but measurable across astronomical distances. If true, this would make Neptune not just a planet, but something else entirely, a hybrid object, governed by both classical mechanics and still unknown forces. But the implications go far beyond Neptune itself. If the data holds up, it suggests that thousands of similar ice giants, cataloged across the galaxy, so-called mini-Neptunes and sub-Neptunes, might also behave in unpredictable ways, undermining assumptions baked into every exoplanet model used today. In short, this isn't just about one planet acting strangely. It's about whether the universe plays by the rules we've written, or whether it's time to rewrite them altogether. And if Newton's laws are merely approximations that collapse under extreme cosmic conditions, what else have we misunderstood? That's the question now, gripping the astrophysics world, and the controversy is just beginning. To understand how serious this is, we need to look deeper into the data. The anomalies in Neptune's orbit aren't dramatic swings or chaotic trajectories. Instead, they're subtle deviations. Minute differences between predicted positions and observed locations, just enough to cast doubt on the assumption that only known gravitational influences are at play. The James Webb Space Telescope has offered the most detailed measurements yet, backed by Earth-based systems like ALMA and the Very Large Array. These instruments have tracked Neptune's position over time and found that it drifts slightly inconsistently and inexplicably. The first theory suggested it might be an external force, a distant, as yet undetected object like the hypothetical Planet 9. But when researchers accounted for all known gravitational actors in the solar system, the numbers still didn't line up. That's when attention turned inward to Neptune itself. Inside this distant ice giant, something strange appears to be happening. Instead of being a layered body of rock ice and gas, recent models suggest Neptune's interior might be a swirling mosaic of exotic zones, including superionic ice, an otherworldly state of water, where hydrogen ions move freely through a lattice of oxygen atoms. It behaves like both a liquid and a solid, conducting electricity, while maintaining crystalline structure. Laboratory simulations have confirmed such states can exist under extreme pressure, but no one expected to find them at planetary scale. These zones don't just challenge material science, they could influence gravitational behavior. If the interior is constantly shifting denser here, lighter there, it might alter the planet's gravitational center just enough to nudge its orbit, especially over long periods. That hypothesis gained traction when researchers noted Neptune's unusual thermal signature. Despite receiving very little sunlight due to its distance, Neptune emits more heat than it absorbs. This excess thermal energy isn't fully explained by known mechanisms like residual heat from formation or tidal heating, but it might be linked to internal friction caused by interacting layers of exotic matter. Adding to the puzzle is Neptune's bizarre magnetic field. Unlike Earth's relatively stable dipole field, Neptune's magnetic field is tilted off-center and in constant flux. It's believed to be generated not by metallic hydrogen like Jupiter, but by those same superionic and plasma-rich zones within the planet's mantle. The magnetism drifts over time, possibly influenced by resonant cavities, hollow chambers of varying density that act like amplifiers for electromagnetic energy. These cavities could be the missing link. If they're real, they might explain not only Neptune's warped magnetic field, but also strange patterns of radio emissions detected recently, bursts that don't match any known atmospheric activity and may be coming from deep inside the planet. Together, these findings paint a picture of Neptune not as a static body, but as a dynamic, chaotic system, one that operates according to rules we're only beginning to glimpse. Now the debate intensifies. Are we simply misinterpreting rare atmospheric events, or are we witnessing the early signs of a paradigm shift in planetary science? What makes Neptune's case so powerful is the convergence of anomalies across multiple domains: orbital irregularities, thermal excess, electromagnetic drift, and unexplained radio emissions. Separately, each could be dismissed. Together, they form a pattern too persistent to ignore. Neil deGrasse Tyson's statement wasn't just a commentary on Neptune. It was a warning that we may be nearing the edge of Newtonian certainty. And some scientists are beginning to echo that sentiment. The idea of exotic matter inside Neptune is particularly provocative. Traditionally, such forms like quark-gluon plasma or Bose-Einstein condensates have only been observed under extreme lab conditions or postulated in theories of the early universe. But if similar states can form inside planets under natural pressure and temperature gradients, it would imply that planetary interiors are far more diverse and more unpredictable than we imagined. That opens the door to a radical reinterpretation of what a planet even is. Could Neptune and planets like it be self-stabilizing systems governed by chaotic internal feedback loops rather than simple gravity and inertia? Some researchers now propose the term chaotic equilibrium bodies to describe celestial objects that regulate their own motion through internal energy redistribution rather than external forces. Under this model, Neptune might be shifting its own orbital path subtly, not because it's being pulled by an outside force, but because its mass center and magnetic field are oscillating due to phase shifts in its internal matter. That's not just science fiction, it's a plausible extension of thermodynamic principles into planetary mechanics. But not everyone is on board. Skeptics argue that what we're seeing could still be explained by undiscovered external masses or a better refinement of gravitational equations, like what happened with Mercury in the 19th century. Back then, Newton's laws seemed to fail until Einstein's theory of general relativity accounted for the curvature of space-time itself. Could Neptune be forcing us into another Einstein moment? It's a tempting parallel. In fact, some theorists are already dusting off extensions of relativity, or looking at quantum gravity models that might explain why Neptune behaves like a planet partially detached from classical physics. Others point to similar anomalies in exoplanet data. If confirmed, this would suggest that what we once considered an oddity may be a class-wide behavior of ice giants, meaning thousands of planets in our galaxy could be governed by internal physics we don't yet understand. Then there's the wild card, the possibility that Neptune is not a uniformly solid planet at all, but contains layered resonant voids or cavities that behave more like oscillating chambers than fixed volumes. These regions could trap and amplify electromagnetic waves, producing measurable radio emissions and subtly influencing how Neptune interacts with solar wind. Imagine it a planet with a literal voice, humming and pulses through space. The implications of this are staggering. If certain planets generate their own internal rhythms that feed back into their motion, we might need to build entirely new models of orbital mechanics, ones that account not just for mass and velocity, but for internal oscillatory dynamics. This wouldn't just rewrite how we study planets, it would redefine what we believe they are. And with Neptune being one of the most commonly used templates for studying exoplanets, a shift here could unravel countless assumptions baked into current planetary classification systems. What we're seeing may be the beginning of a quiet revolution, one not declared by a single discovery, but whispered across a pattern of data too strange to ignore. If Neptune truly defies Newton, the implications ripple far beyond our own solar system. For decades, planetary scientists have used Neptune as a blueprint to classify and model exoplanets, especially the so-called mini-Neptunes and sub-Neptunes that now dominate exoplanet catalogs. These distant worlds were assumed to behave similarly to their namesake: dense cores, icy mantles, gas envelopes, and stable orbits. But what if those assumptions were wrong from the start? What if these planets are not Neptunian in the way we've always believed, but belong to a far more chaotic and complex class planets that pulse drift, resonate, and evolve from the inside out? If Neptune is a hybrid object, not just an ice giant, but a thermodynamically active system influenced by exotic physics, then our entire approach to planetary classification, habitability modeling, and even deep space navigation may need revision. And there's more. The newfound radio emissions from Neptune, strange, impulsive, and seemingly sourced from deep within, add a layer of mystery we're just beginning to unpack. Unlike the well-understood radio bursts from Jupiter or Saturn caused by solar wind interactions, Neptune's emissions don't fit the known mold. They behave more like intermittent signals, possibly tied to internal electromagnetic resonances bouncing between stratified layers or trapped within pressure chambers deep below the cloud tops. Could these emissions be the acoustic echoes of internal instability or evidence of unknown quantum-scale processes at work inside the planet? Some researchers have dared to speculate that Neptune might represent the first observable living planetary system, not alive in a biological sense, but in its dynamic responsiveness to internal and external forces. In this light, Neptune becomes more than just a distant blue gas giant. It becomes a testing ground for new physics. But what if we're wrong? What if there's no exotic matter, no internal chaos, no hybrid structure? What if the deviations are simply the result of our own observational limitations, or an unknown body like Planet 9 pulling strings from the shadows? That too would be profound. It would mean that our solar system remains incomplete, still harboring secrets beyond the reach of our most advanced instruments. Either outcome, new physics, or unseen mass fundamentally challenges our picture of the cosmos. And that's the real story here. Not just that Neptune behaves strangely, but that we in 2025, with all our telescopes, simulations, and theories, still don't fully understand the world next door. We are reminded once again that the universe is not obligated to conform to our expectations. The question now isn't just what Neptune is, it's what else are we missing, and how much of what we think we know is built on sand. So here's the question for you. If Neptune no longer obeys the rules, are we ready to admit that maybe, just maybe, the rules themselves were never complete to begin with?